Okay, so we have a question. Consider a market with two horizontally differentiated firms, X and Y. Each has a constant marginal cost of $20. Calculate the Bertrand equilibrium in prices in this market. So, break down the question a bit. You have a market with two horizontally differentiated firms. Horizontal differentiation is essentially just means that the product is perceived by customers as not being absolutely better than the other product, which implies that if one firm raises their price, they won't lose all their customers to the other firm. So there's differentiation in the products. So they're not perfect substitutes. Substitutes. And we have a demand functions of Qx and Qy pertaining to firm X and firm Y. And so we want to calculate the Bertrand equilibrium in prices, and Bertrand equilibrium is a price competition, essentially. But when they're differentiated, it is softer. So, like I said before, you won't lose all your customers if you raise your price a bit, because customers are loyal to you. They have their own preferences. They're not indifferent. So, you want to maximize the profit that will equal uh, and so I'll try to keep it on the lines. So that's actually not timesing that. You want your price cost margin. So PX minus 20. And that is all good. Yeah, okay. minus 20 py. Just distribute the px and the negative 20 into the all three terms here. Then you combine like terms. I haven't done this one either, so you're kind of coming along for the ride with me, which is why it won't be as great. And it might not be. So you have 100 px there, you have 40 px there. Every other term, you have a constant, two variables, and a coefficient and a variable no. And 100 plus 40 is 140 px. Minus 20 py. Then you're going to take the partial derivative with respect to px. And so 1, so px you have 140 minus 4 px plus py is the partial derivative. So px disappears, and these two are not in terms of px, so they are not there. And setting that equal to 0, for px you have 140 plus py equals 4px, dividing through by 4. We have 35 plus 0.25 py. And that is firm X's best response function for py. Now, in order to solve this for the best possible price, we will have to solve for py, for qy, firm y, all the same thing. I did that in blue. I probably should have kept that in green, but whatever. Let's keep it consistent. So, the line that I start on, this one, you'll have your profits for y, max in and out, is price times quantity minus, well, multiplied through your price minus your marginal cost. Plus px multiplied through $20. So I'm trying to keep it all in one line. $100 times negative 20, so like same thing. They're basically going to be they're actually symmetrical. So I'm actually going to end up with the exact same thing. So I could just copy and paste, but I'll show you the workings. 2000 negative 2py into a negative is positive 40py, and px into negative 20 is negative 20px. Should be on the same line. It is not. Okay, that's okay. I was gonna try and do a cool side by side little there. Okay, let's ignore that one. Why does it push it up? I don't get it. Okay, so I've just rearranged it a bit. And highlighting blue, highlighting like terms. But like I said before, this is just going to be the exact same thing. So you're going to have and that is all combined. So then taking the partial derivative with respect to py this time, so that equals insert, you get 140 minus 4py plus px, setting that equal to 0. And dividing through by 4. And now, substituting this one, in for py there. So I want to kind of keep it and similarly to the corner model, everything is now in terms of px, which is good because then you can solve. Do not add these together first. This is the a fraction, you should need to multiply that through first before you add them together. Otherwise, you will not get the right result. So that's and it's all going to be positive. There's no negatives. 35 is 8.75 plus a quarter times a quarter is 0.0625 px, and you're kind of looking for smaller numbers when you get to this point, because you're going to solve for px. So you get and dividing through by that decimal over there. 306.25 divided by 0.9375. Get 326. 326.67. That is your price. That is what we're looking for in the question. The price that the firm X is going to charge is $326.67. And now doing the same thing over here, you will get, they each have a constant marginal cost of 20 though. That's what really that's where your answers differ, is when, well, if your demand curve is different or demand function is different, but if your cost structure is different as well. These seem to be symmetrical. Just double check. I know it's simultaneous, but sometimes you can forget. 35.25. And getting the same result. Wait, is this the same result? Ah, okay. So you have 2py. Oh no. Did I make a mistake there? I did make a mistake. Okay, so this is wrong. I hit the multiplication button and not the addition button when summing those. So even though they're differentiated, just fixing that up, they will have the same cost, the same price. So Bertrand equilibrium price will be 46.67 for each firm. Okay, so in graphing this, you'll get in blue. I'll just do the price here, close to the middle because it's close to 50. Far out. Oh god. Okay, just gonna leave that there. And for PY I'll have 35. I'm gonna put that there. And you'll get an intersection point for the prices of each. Be right there, as well as some lines for each firm that both slope upwards. And that is what you're going to be left with in terms of the intersection point. Which is there.